Now we will study how to design the domestic water supply system and how to select the pressure booster pump for a high-rise building. We already studied selection of domestic water piping inside the buildings. Now we will concentrate for risers and main lines only. To make easy to understand, I will do a sample exercise for a 10-story building having 10 apartments on each floor and each floor height is 10 feet. There are 5 numbers of main water supply risers R1, R2, R3, R4 and R5. Each riser serving 2 apartments on each floor. Each apartment has 2 bathroom groups and 1 kitchen sink. When we have a bathroom for our personal use, having shower, 1 WC, 1 wash basin, then we call it as bathroom group because it will be used by a person and one fixture will use only one time. To make our study simple, we have assumed that all the risers are typical. Then we will select the farthest riser, which is riser number 5, that will have the longest piping route and will have the maximum pressure drop. If your risers are not similar, then you need to repeat your calculation for each riser. Then piping having the largest pressure drop should be selected to design the water supply system and for the selection of booster pump for that building. As we are designing the main water supply line, so we will use the total load values. For bathroom group, we have total load value 3.6 water supply fixer unit and for kitchen sink 1.4. As we have 2 bathroom group in one apartment, so 3.6 into 2 equal to 7.2, and we have one kitchen sink also, so we will add it. The total value for kitchen sink 1.4, so plus 1.4, then it will be equal to 8.6. As one riser is serving 2 apartments on each floor, then the load value for one riser on each floor will be 8.6 into 2 and it will be equal to 17.2 water supply fixer unit. In our study, we have assumed that each apartment is using its own electric water heater. If you are designing a building having central hot water system, then you need to make calculation for hot water risers also to find the route for maximum pressure drop. Later on, we will make a study having central hot water system also. If we draw a riser diagram, then you can see at the top of the riser, that is at the 10th floor, this riser is supplying water to 2 number of apartment. When we came down the lower floor to 9th floor, then this riser is supplying water to 4 number of apartment. As we go down, the number of apartment is increases. When we go the lowest floor, ground floor, then this riser is supplying water to 20 number of apartment. In this way, we can see this riser has 10 segment and each segment has different load values. You can see the segment at 10th floor is having 17.2 load value, the segment at 9th floor is having 34.4 and the segment at floor is 51.6. When we came down to the ground floor, it is having 172. So each segment will have different GPM and resulting different pipe size. Let us select the critical path, which is in our case is the longest route to which the riser number 5 is connected, to calculate the maximum pressure drop in the piping route. You can see we have different pipe segment also at the basement. This pipe segment have water supply fixer unit 172 and length 60 feet. This segment water supply fixer unit 344 and the length is 60 feet. Another segment 516 water supply fixer unit and length of 60 feet. And the main line is having 860 water supply fixer unit. Let us assume this length of 30 feet. Let us make a table in Excel for all the pipe segment. Then we will select the corresponding GPM for all water supply fixture unit using table 103.33 of International Plumbing Code. Then we will select the corresponding pipe size, velocity and pressure drop per 100 feet from hydraulic table using ASPE handbook. Then we will calculate the total pipe friction loss in the critical path. Let us select the GPM. But there will be one problem. You can see our load values are 17.2 water supply fixture unit, 34.4, 51.6, 68.8, and it go up to 516 and 860. When we go to table 103.33 to select the corresponding GPM, you can see we have the in this list in column we have the water supply fixture unit value 17, then 18. Our value is 17.2. Then the next value for us is 34.4, but here you can see we have the water supply fixture unit value 30 and 35. Similarly for other values we have 50 and 60. Our value is 51.6. Then we have 103.2, but here you can find only 100, then after this 120. To overcome this problem, we will use linear interpolation formula at least to get the nearest value if not exact. Our first load value is 17.2 water supply fixture unit. For 17 water supply fixture unit we need GPM 18.4, and for 18 water supply fixture unit we need GPM 18.8. Applying linear interpolation formula, we need the GPM for 17 water supply fixture unit, it is 18.4, and for 18 water supply fixture unit we have the GPM 18.8. Then for 17.2 we will need the GPM 18.48. Second load value is 34.4 water supply fixture unit. For 30 water supply fixture unit we need 23.3 GPM, and for 35 water supply fixture unit we need 24.9 GPM. Similarly for 34.4, for 30 water supply fixture unit we have the GPM value 23.3, and for 35 we need the GPM 24.9. Then the GPM needed for 34.4 water supply fixture unit will be 24.708. Now select the GPM for segment 8, load value 137.6. To select GPM for 137.6 water supply fixture unit, we have value for 120 and 140. For 120 water supply fixture unit we need 48 GPM, and for 140 water supply fixture unit we need 52.5 GPM. For 137.6 we need the value for 120 and 140. So let us apply the formula. For 120 we need the GPM 48, and for 140 we need the GPM 52.5. Then the GPM needed for 137.6 water supply fixture unit is 51.96. And last load value is 860 water supply fixture unit. To select GPM for the last values 860 water supply fixture unit, we have 750 water supply fixture unit, and the GPM needed for it 170, and 1000 water supply fixture unit we need the GPM 208. Similarly, to select the GPM for 860 water supply fixture unit, we know the value for 750, it is 170, and for 1000 it is 208. Then the GPM needed for 860 water supply fixture unit is 186.72. Similarly, we can select the GPM for all the segment. After calculating the GPM, the next step is to select the pipe size. Before pipe sizing, you need to select the piping material. For our example, we will use the copper pipe type K. For domestic water pipe sizing, we follow these rules. For cold water piping, the maximum velocity limit is from 4 to 8 feet per second and the maximum pressure drop limit is 5 psi per 100 feet. For hot water piping, the maximum velocity limit is 5 feet per second and the pressure drop limit is 5 psi per 100 feet. When we will select the pipe size for the GPM, again we will face the same problem like we face when we select the GPM from the load values. Our GPM values is 18.48, 24.7, 29.56 and up to 186.72. But in hydraulic table we will not find these values, so we will use the same linear interpolation formula to find the nearest value if it is not exact. Each pipe size has its own hydraulic table. This table is for a pipe size 1¼ inch. The first column is for the GPM and there are other columns as per the material. You can see this column is for schedule 40 steel pipe, this for schedule 80 steel pipe. We are using copper pipe type K, so this column is for us. Inside this column also there is two sub columns. The first column is for the velocity in feet per second and the second column is head loss psi per 100 feet. Our first GPM value is 18.48. Our first GPM is 18.48. So let us first try to select 1 inch pipe size. So we will use the hydraulic table for 1 inch pipe. Here you can see we have a value for 18 GPM and for 20 GPM. For 18 GPM, let us select the copper pipe type K. So the velocity will be for 18 GPM 7.42 and for 20 GPM the velocity will be 8.24, which is more than the maximum limit 8 feet per second. When we see the head loss per psi per 100 feet, for 18 GPM this is 11.9 and for 20 GPM this is 14.5. These both values are much higher than the maximum limit, which is 5 psi per 100 feet. So we cannot select the 1 inch pipe size. Then we will go next pipe size, which is 1¼ inch. Now it is the hydraulic table for the pipe size 1¼ inch. We can find here 15 GPM and the velocity for 15 GPM for copper pipe type K is 3.95 and for 20 GPM it is 5.26, which is less than the limit 8 feet per second. When we see the head loss, it is for 15 GPM 2.9 and for 20 GPM 4.9. Both values are less than the maximum limit, which is 5 psi per 100 feet. So for 18.48 GPM we can select the 1¼ inch pipe. To select the exact pressure drop and velocity, again we will use the interpolation formula. For 15 GPM we have the velocity 3.95 feet per second and for 20 GPM we have the velocity 5.26. Then for 18.48 we will have the velocity 4.86. Similarly for 15 GPM in 1¼ pipe we have pressure drop 2.9 psi per 100 feet and for 20 GPM we have pressure drop 4.9 feet per 100 psi per 100 feet. Then for 48.48 GPM we will have a pressure drop of 4.29 psi per 100 feet. Now we can update this value in our Excel sheet. For load value 17.2, GPM is 18.48 and the pipe size we need 1¼ inch. The velocity will be there 4.86 feet per second and the pressure drop per 100 feet will be 4.29. Second GPM value is 24.71. For 24.71 GPM, let us select the 1.5 inch pipe. Here we have 20 GPM and 25 GPM. For 20 GPM, we have the velocity for copper pipe type K 3.72, and for 25 GPM we have the slug velocity 4.65. Both are in the range. Then head loss PSI per 100 feet. For 20 GPM it is 2.1, and for 25 GPM it is 3.2. So we will select the 1.5 inch pipe for 24.7 GPM. For exact value of velocity and head loss, again we will use the interpolation formula. For 20 GPM the velocity is 3.72, and for 25 GPM the velocity is 4.65. Then the velocity for 24.71 will be 4.596, or we can take it 4.6 feet per second. Similarly, for head loss, for 20 GPM we have the head loss 2.1 psi per 100 feet, and for 25 GPM we have the head loss 3.2. So for 24.71 we have the head loss 3.136, it means 3.14. Let us fill these calculated value in our Excel sheet. For 34.4 water supply fixture unit, we need the GPM 24.71 and the pipe size 1.5 inch, and the velocity is 4.6 feet per second, and the pressure drop is 3.14 psi per 100 feet. Segment 11 we have GPM value 93.8. Let us select the pipe segment 11 having GPM 93.8. We will select for it 2.5 inch pipe size. So in this table we can see we have 90 GPM and 100 GPM. Let us check for both GPM. For 90 GPM we have the velocity for copper pipe type K 6.2, and for 100 GPM we have the velocity 6.89. Both are inside the limit, maximum limit. We have 8 feet per second. For the pressure drop, for 90 GPM we have 3 psi per 100 feet, and for the 100 GPM we have 3.7 psi per 100 feet. So these both values are inside the maximum limit. So we can select the pipe size 2.5 inch for a GPM 93.8. To calculate the exact value of velocity and head loss, again we need to do the exercise linear interpolation formula. For 90 GPM we have the velocity 6.2 feet per second, and for 100 GPM we have the velocity 6.89. Then for 93.8 GPM we will have the velocity 6.46 feet per second. Similarly, for 90 GPM we have the head loss 3 psi per 100 feet, and for 100 GPM we have the head loss 3.7 psi per 100 feet. Then for 93.8 GPM we will have the head loss 3.266, or we can take it 3.27 psi per 100 feet. Let us again fill these values. For pipe segment 11, for load value 344 water supply fixture unit, we need GPM 93.8, and we will select the pipe size 2.5 inch with velocity 6.46 feet per second, and the head loss 3.27 psi per 100 feet. And the last main pipe GPM is 186.72. For our last pipe segment we have the GPM value 186.72 Let us check if we can select the 4-inch pipe size for it. In this table we can find 180 and 190. So let us select these both rows, and we can see for 180 the velocity is for copper pipe type K 4.94, and for 190 the velocity is 5.21. When we go for the head loss is for 180 GPM 1.2, and for 190 it is 1.3. All values are within the maximum limit. Velocity are less than 8 feet per second, and the head loss is less than 5 psi per 100 feet. So we can select the 4-inch pipe for 186.72 GPM. To calculate the exact velocity and head loss, again we need to go for linear interpolation formula. For 180 we have the velocity 4.95, and for 190 we have the velocity 5.21. So for 186.72 we will have the velocity 5.12 feet per second. Similarly, for 180 GPM we have the head loss 1.2, and for 190 GPM we have the head loss 1.3. Then for 186.72 GPM we will have the head loss 1.267, or we can take it 1.27 psi per 100 feet. Again, let us fill these calculated values in our Excel sheet. For a load value 860 we need GPM 186.72, and we have selected the pipe 4 inch with a velocity 5.12 feet per second, and with a head loss of 1.27 psi per 100 feet. In the same way, we can select the pipe size, velocity and pressure drop for all other sizes, and we have calculated these values. Let us fill the each pipe segment length. As our floor height is 10 feet, so we will have each pipe segment of 10 feet. Let us put 10 here, 10, 10, 10. For pipe segment 10 we will have vertical height 10, and horizontal also we have 60, so it will be 70. For pipe segment 11 and 12 we will have 60 feet, and for pipe segment this last pipe segment we assume it as 30 feet. So the total friction pressure loss in our piping will be 9.127 psi. Let us assume inside the building the fixture that need maximum pressure is WC, and it is located 30 feet away from the riser. So assuming this pipe sizing inside the building at maximum friction loss 5 psi per 100 feet, so the pressure loss in 30 feet of pipe will be 1.5 psi, and the total pressure loss will be 10.627. As per normal practice for fittings and walls, we add 50% to the pipe friction loss, so the net total pipe friction loss will be 15.94 psi. Now we will calculate the pressure drop due to elevation difference. As we know, our building is of 10 floor and each floor height is 10 feet. So 10 into 10 equal to 100 feet. Our building height is 100 feet. And as we know the formula for the elevation difference, each foot of vertical rise is equivalent to 0.434 psi pressure drop. If we are lifting the water to 1 feet, then the pressure drop will be 0.434 psi. If we will lift the water to 100 feet, Then we need to multiply this 0.434 by 100, then we will get the result 43.4 psi. So when we will transfer the water from basement up to the top floor, the pressure loss will be 43.4 psi. Friction loss inside the pipe we already calculated, and its value is 15.94 psi. In the main line we have two devices, one backflow preventer and one water meter. Let us assume pressure drop inside the backflow preventer is 0.9 psi and pressure drop inside water meter 3 psi, and pressure required for the last fixture, that is WC with flush tank, equal to 20 psi, and considering for future allowance of 30 psi, then net total pressure drop inside the system will be 113.24 psi. The total pressure drop in the system is equal to 113.24 psi, and the total water needed for the building is 186.72, or we can take it as 187 GPa. If we are using direct supply system with available municipality water head of 40 psi, then this 40 psi we need to subtract from the total loss 113.24 minus 40, and it will be equal to 73.24 psi. If we need to convert this value into water head, then we need to multiply this value by 2.31. So 73.24 into 2.31 will be equal to 169.18 feet of water head. So we need to select the booster pump with a capacity of 187 GPM, having a water head of 169 feet. If we are using the water tank at the ground level, then we will not add the loss in water meter and backflow preventer. So subtracting this loss value from the total pipe loss, 113.24 minus 3.9, then it will be equal to 109.34 psi. If we need to convert this pressure loss into water head, then we need to multiply this value by 2.31, and we will get the result 252.58, or we can take it 253 water head in feet. So we need to select a booster pump with a capacity of 187 GPM with a water head of 253 feet. If we need to calculate this pump capacity in horsepower, so then we have two formula. One formula is HP equal to H into Q into SG divided by 3960, where H is the head in feet, Q is the flow rate in GPM, and SG is the specific gravity. For water it is 1. Another formula is HP equal to P into Q into SG divided by 1714, where P is the pressure in PSI, Q is the flow in GPM, and SG equal to 1 for water. As we have calculated the value for the pressure loss, it is equal to 113 psi, and we need the GPM 187. When we apply this value in the formula, 113 into 187 divided by 1714, the result will be 12.33. So the horsepower will be 12.33. If our pump efficiency is 70%, then we will divide this value by 0.7, then we will get the required horsepower for the pump 17.61 HP. So we need to select the booster pump with capacity of 17.61 HP. In normal practice, when we design domestic water system for a high-rise building, we divide it into zones, and general practice is 6 floors in one zone, and it depends on the height of the floor also. Then we select the separate booster pump for each zone. In this picture you can see we have a building of 10 floors, and we divide it into two zones. The lower zone having 3 floors, and the second zone is having 7 floors, and we have selected different booster pump for both zones. Generally for the lower floors we do not use the booster pump, and we design it utilizing the available pressure from municipality. In our next video, we will make a simple exercise for this system. Sometimes we use series connected system with intermediate break tanks to supply the water for different zones, and sometimes we use series connected system without intermediate break tanks. Sometimes we use overhead water tank. In this system, first we use the booster pump to supply water from basement up to the top floor water tank. Then for upper floors we need to use the small booster pump to provide the sufficient water pressure for the upper floors. Later on we will study all these systems in detail one by one. I hope this video will help you. Thank you very much.